I'm gonna attempt to prove the parallel axis theorem. This isn't like, I don't think this is a formal proof because like I'm only using the example of like a hoop because it's easier. But I'm gonna at least show you that where the equation comes from. And the equation, if you're unfamiliar, is saying that the rotational inertia of an object about some axis, right, is equal to its rotational inertia around the axis of its center of mass, about its center of mass, plus the mass times d squared. D being the distance between the two axes. And they gotta be parallel, right? So for a hoop rotating like this way, right, the axis is pointing out of the page, or like, into out of the page, and then this axis is also into out of the page. So they got to be parallel for this to work. But that's what we're gonna at least attempt to kind of prove or show or whatever you want to call it. What is the definition of rotational inertia? Like on the equation sheet, it's saying that it is the integral of r squared with respect to the mass. So, if you think about a point mass, right, it's rotational inertia. So if you want to see where this comes from, it's like, a point mass has a rotational inertia mr squared. So for a very small amount of dm, if you had a very small section of the ring dm, that is going to create a small amount of rotational inertia, which is equal to mr squared, which in this case is dm times r squared. And then, to get the full thing, we integrate both sides. So you get I is equal to integral r squared dm. So we got to basically take that integral for this case. So to make this easy, we can kind of find the distance of the, that, so like if I'm doing it for this dm, right? So this dm right here, we can find that distance, right, from the center of mass, right? R is just the distance from that axis. I'm saying center of mass, I meant this new axis. So we'll call that R. So if you think about it in terms of theta, right, let me kind of show this. So it's just geometry. I'm about to do some geometry here. Because if this is an angle theta, right, we know this is going to be a right triangle. This component is going to be r sine theta, and this component is going to be r cosine theta. So hopefully you're comfortable with that. Right, I'm just using trig to kind of figure it out. So if we were to figure out the r for a certain dm, right, the distance from the new axis to that infinitesimally small dm, we can kind of use geometry and be like, well, this right here, it's kind of hard to see, but this forms a right triangle, and then this here, I'll actually just fill in. This right here forms its own right triangle, right here. So if I just use Pythagorean theorem, r squared is going to equal r sine theta squared. So I'll just say r squared sine squared theta, plus now this leg of the triangle, which is really just d. So if I were to do this, it's really just the full distance d minus this part of the of that, what do you call it, like component, this part of the radial component, I don't know what you call it, it's minus the r cosine theta. So the reason I'm doing this is because eventually what's going to happen is I can find dm in terms of d theta, and then I can integrate with respect to theta, right? So if I, this is r squared, and this works for like, if theta is equal to 0, so for this point right here, theta is equal to 0, so sine theta is equal to 0, this cancels out, cosine theta is equal to 1, so you get d minus r, so that r squared is just equal to d minus r squared, or r is equal to d minus r. So it works like kind of for every angle. Let's substitute that back in. So I is equal to integral, let's do r squared sine squared theta plus d minus r cosine theta squared dm. So we still have that dm in there. How are we going to get rid of it? Well, for a thin hoop, we can, for a thin hoop, its linear mass density is constant. So if I say lambda is equal to the linear mass density just means the amount of mass per length. So I can just do m over the length, which is the circumference, 2 pi r. So lambda is equal to m over 2 pi r. Well, it's also going to be equal to lambda m, which is dm, over a very short amount of length, which would be dl or whatever, right? dl, a small amount of length, is really just an arc length on this circle, and our equation for an arc length of a circle is equal to theta times r. So for a very small I'm mixing up my words. For a very small arc length, that length is just equal to d theta times r, and then I can just say dm is equal to lambda d theta times r, or lambda r d theta. So I can even now rewrite this and say, okay, I is equal to integral of r squared sine squared theta plus d minus r cosine theta squared, right? And then instead of dm, I could say lambda d theta, or lambda r d theta. So lambda r d theta. Okay. So, and this should really be a capital R because it's the radius of the circle. So now you can take this integral. To take this integral, you could separate each part. So I could say, well, I is equal to integral r squared sine squared theta times lambda r d theta plus integral of d minus r cosine theta squared lambda r d theta. So for this one, if you remember, you can the integral of sine squared theta d theta. I can really quickly show it here, in case you don't know. So I could say integral of sine squared theta d theta. This is the same thing as integral. If you use that cosine 2x is equal to 1 minus 2 sine squared x, you can solve for sine squared x by adding, so it would be 1 minus cosine theta over 2 d theta, 2 theta. And then you can do your and then you can you could do like you could solve this from there by separating it and then doing your u sub, but you'll get that it's equal to, and I'll just write it here because I started it, but I realized I really didn't need to do this. It's really just equal to theta r minus sine, not theta over r, what am I doing? Theta over 2 minus sine 2 theta over 4 plus c. Yeah, that makes sense. So I could say I is equal to, and I got to do my bounds, right? So for theta, I'm integrating from the whole circle, which is going to be from 0 to 2 pi. So it's going to be equal to, well, if I'm integrating from 0, I can just plug in 2 pi for theta. So I get 2 pi over 2 minus sine 2 theta, so sine 2 theta, that would be 4 pi over 4. No plus c, and this kind of becomes 0, right? Because sine of 4 pi is 0. So now I can do this integral. Well, I should probably actually first expand this one more time. So if I expand this polynomial, in fact, what I could just do, just to make this easier, oh yeah, because I forgot this stuff too. So I should probably make it a little bit easy. I can pull out, first of all, I can pull out a lambda r from both these integrals. And then what I can do is once I pull out the lambda r, for this part of the integral, it's really just r squared, and then just what I wrote, so so 2 pi over 2 minus sine 4 pi over 4. And then for the next part, this is really just the integral from 0 to 2 pi d squared minus 2rd cosine theta plus r squared cosine squared theta, all of that, d theta. So now what I can do, and then let me finish up my parentheses, I is equal to lambda r. Now I'm going to have r squared. I'll just write pi r squared, right? Because this is sine 4 pi over 4, but the sine 4 pi is 0, so it's just, I can write it as pi r squared. So pi r squared plus, now for this integral, you could kind of do each part. So d squared d theta would be just, it would be d squared times 2 pi, because d squared is a constant, so it's just 2 pi d squared. For this part, the antiderivative of cosine is sine, so I could say it's minus 2 times r times d. Now I'm doing cosine theta, but the bounds are 2 pi to 0, so it's really cosine 2 pi minus cosine 0. But cosine 2 pi is equal to cosine 0. They're both equal to 1. 1 minus 1 is 0. So this term, it will actually end up canceling. And I'll show that. Actually, I guess I should be more clear. 2rd cosine 2 pi minus cosine 0. Okay, so, and then this last part, it's pretty similar to this integral, except you would add, so it would be plus now r squared just making sure I didn't mess this up. Yeah, okay, I didn't mess this up. So r squared now, cosine squared theta, it's this stuff, so it would be pi plus sine 4 pi over 4. Okay, now this is going to start simplifying. So I is equal to lambda r. We have pi r squared plus 2 pi d squared. This is equal to 0. So this whole thing, this whole thing is equal to 0. And then this is equal to, this part is also equal to 0. So it'd be now pi plus pi r squared. There's 2 of them though, so I could really just write 2 pi r squared. So I kind of wanted to keep that pi. I'll just do it. So pi r squared plus 2 pi d squared plus pi r squared. So I is equal to lambda r 2 pi r squared plus 2 pi d squared. But remember lambda is just equal to m over 2 pi r. So I could say I is equal to lambda m over 2 pi r. I don't know why I said lambda. So times r. So what you notice is those r's are going to drop out over 2 pi r squared plus 2 pi d squared. So now the r's drop, and then we're going to distribute to each. So we're going to say I is equal to m over 2 pi times 2 pi r squared plus m over 2 pi times 2 pi d squared. The 2 pi's drop, and you can see pretty clearly, if we go now to I equals, and then it's going to be m r squared plus m d squared. So there you go, right? So mr squared, that's just, wait, this is the wrong marker. Mr squared is just the rotational inertia of a disk about its center of mass. So this would be ICM of disk, and then this is the md squared part. So obviously, I showed it for a hoop, so this isn't really a formal proof, but this could work. You could do this for any shape you wanted, and you would get the same result. You could try to find a formal proof online. I'm sure they're out there. Probably a lot of complex math, but it's pretty cool stuff. So there you go. Hopefully this video was at least kind of interesting. I don't know, because this was kind of long, but yeah, hopefully this was good. Thank you for watching. I appreciate it.